Hi class. Earlier, we briefly mentioned type 1 errors when discussing the test of significance. Now, let's go deeper. In fact, there are two types of errors in statistics, type 1 and type 2 errors. Remember, errors are inevitable because we use samples to make inferences about the population. Samples are only a small fraction of the population. So statistical decisions are always based on probability estimates. The chart on the left shows the four possible outcomes when we make a decision in hypothesis testing. If the null hypothesis is true, but we reject it, this is a false positive, also known as a type 1 error. The probability of making a type 1 error is the alpha value that we set proactively. On the other hand, if we decide not to reject a true null hypothesis, that is a correct decision. The probability of this true negative outcome is 1 minus alpha. Now, if the null hypothesis is false and the evidence leads us to reject it, that is another correct decision. The probability of this true positive outcome is 1 minus beta. Here, beta is the probability of failing to reject a false null hypothesis, and this mistake is called a type 2 error. Unlike alpha, which we set in advance, the probability of making a type 2 error is not as easy to determine. Ideally, we would want to minimize both types of errors in our research investigations. However, here's the dilemma. Lowering the likelihood of one type of error usually increases the likelihood of the other. So, as a researcher, you must make a value judgment about balancing these risks. Three key questions to consider are: first, what would be the consequences of making a type 1 error? Second, what would be the consequences of making a type 2 error? And third, which type of error do you have a higher tolerance for? Let's go through an example. Imagine that in a clinical study, a researcher is investigating the effectiveness of a new drug. She compares the symptoms of patients who received the new drug with a control group without treatment. Using a t-test, she obtains a p-value of 0.035. Because this value is less than alpha 0.05, she concludes that the effect is statistically significant and rejects the null hypothesis. But remember, a p-value of 0.035 means that there is still a 3.5% chance of getting these results if the null hypothesis is actually true. In other words, there's still a risk of making a type 1 error. If the conclusion is incorrect and the new drug is truly ineffective, the consequences could be serious. Millions of patients might be prescribed the drug despite risks of severe side effects and inadequate research. This also means that other, potentially more effective treatments would be overlooked in favor of this one. Now, let's look at the other side. Suppose the researcher conducted a power analysis before the study to determine the chance of detecting an effect of given size with her sample. She set the expected effect size at 20%. Meaning the drug reduces symptoms by 20% more than the control treatment. However, if the true effect exists but it's smaller than 20%. Her study design might not detect it because of insufficient statistical power. In that case, she would fail to reject the null hypothesis and commit a type 2 error. The consequence here is different. The drug might truly help patients by improving symptoms, but it would be labeled as ineffective. As a result, a medication with meaningful clinical benefits would never reach the patients who could genuinely benefit from it. So, if you were this researcher, how would you balance the benefits and the risks? This is the essential challenge when dealing with type 1 and type 2 errors.